Welcome everyone to my class on formal methods for system verification. In today's class, we will learn Büchi Automata. So, if you recollect from the previous class, in the previous class we talked about how we actually developed the model checking algorithm for LTL, right? And we have basically have seen that for LTL we cannot use the CTL style model checker where you can actually do the labels, the nodes with different sub formulas, and you try to propagate and try to get a fixed point. So, that philosophy won't work for LTL model checking because it is basically the LTL properties are defined over path. So, then what we have discussed effectively that what we do, we take the formula that on which I want to check on a model or a transition system. So, I will take the negation of the formula and then I will convert that formula into a generalized non-deterministic Büchi automata GNBA, right, and then we will compose, then we convert that GNBA to NBA non-deterministic Büchi automata, and then I will compose that automata with the transition system on which I am actually checking the property, right. And then in the product system, if there is any accepting run, then I will say this actual original formula is not accepted by the model, right. So, this is the overall process that we talked about in the previous class, but to understand the entire process we have to understand what is Büchi automata, what is non-deterministic Büchi automata, what is generalized non-deterministic Büchi automata, right, and those are the things we are going to cover in today's class and the next class. So, we will not go in much technical detail, but we try to convey the actual message on Büchi automata. So, basically in this Büchi automata is related to the infinite words, right. So, effectively if you see that this Büchi automata is something accepts or reject infinite words, right. So, the language accepted by the Büchi automata is infinite words. But now let us understand what is infinite words and finite words, right. So, we are mostly habituated with the finite words, and we know that this regular language, which is basically a set of finite or infinite number of finite words, which is represented by the regular expression, and you have deterministic finite automata or non-deterministic finite automata that accepts or rejects that language, right. And we also know that NFA and DFA is equally powerful, right. So, what usually happen here when you basically give a word, finite word, let us say you give A, B, right, and you have a transition system which is basically have some states and transition, right, some initial state and some final states. And if you basically give this and this basically the transition is labeled with some levels, right. Let me give a concrete example probably, let me take a concrete example. Let I have a DFA like this, which is basically, let us say if you have giving B, it rotates here. If you give A, so this is say S0, this is S1, you give come here, and if you give B here, it will remain here, and if you give A, it comes back to this. So, this is deterministic finite automata because for every state, for every symbol A and B, so in my example there are two symbol A and B, I have transitions, right. In this state if you give A, it will go to this state S1, and if you give B, it will remain in this state. So, this is a DFA, and let's say this is the start states and this is the final state, okay. Now, what are the kind of word it will accept? Let us say if you are giving A, if you are giving AB, right. So, it will come to this state and it stay here, right. So, that means this word is accepted by this finite automata. So, what is the idea here? If you give the word, then eventually after reading this word, traversing the FSM, this finite automata, it will reach to the final state. So, that is what is happening here. So, you will get many such words, right. So, this is AB, which may be B, AB, right, BB, A, right. It can be A, B, 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 right. So, there are many, there will be infinite number of words which will be accepted by this particular automata, and you see every word is finite, it has finite number of alphabets, right. So, these are the finite words, and the automata that accepts this kind of finite words is basically deterministic finite automata. Then what is infinite word? Maybe if, here let us say if you give A, B, so it will come here and then it will go here and then it will remain here, right, AAB. And so this AAB is not accepted by this word, right. So, we will basically identify a set of word which is accepted by this, and there will be set of words which is not accepted by this, by just checking whether giving this input word, or when I reach this, I read the entire word, whether I reach to the final state or not, right. If it is not, then this is not, the word is not accepted by this, right. So, now let us move to the infinite words. So, infinite word is something where the word is not of finite length, it is always infinite. You think about this A and all, right, AB, AB, AB and all. So, this is basically an infinite length, okay. So, this is what is basically infinite words. We usually denote it by this word omega, right. So, this omega actually specify the infiniteness of the word. So, for example, here I have written this AB omega, it means it is a infinite occurrence of AB. It is basically AB, 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 AB and so on. It is the infinite occurrence of the AB, right. Similarly, so the language is basically corresponding to this infinite word is called omega regular language, right. So, earlier the finite words are regular language, infinite words are basically omega regular language, and it basically consists of set of finite words, right. So, what I can do, I can write this omega regular language consists of infinite words, and this omega regular language is written as a combination of set of regular expressions, right. So, where this it is basically AI into Fi omega or A2 F2 omega or so on, and then An Fn omega. Here all these AIs, right, AIs and Fis are basically regular expression, and only thing is that here this Fi, F2, Fn, these are infinite occurrence, right. So, this is a generic way of writing the omega regular language, which is basically consist of set of regular language and their combinations, right, where some regular language is actually occurring infinite times, okay. So, the semantics I can define the omega regular language is basically union of this or this, right. This is corresponding to A2, language of A2 into language of F2 omega union and so on, right. So, this is how I can define the omega regular language, but in a layman term it is basically infinite words which is having a sub expressions which is basically regular expressions, right. So, few example of this omega regular languages. So, this I have already explained. If I write this A star B omega, it means I have a finite occurrence of A followed by infinite occurrence of B, right. So, there are word like, if you think about this, so you have A, B, B, B. So, B has always infinite occurrence, but the occurrence of B, A is finite, right. It can be A, then B, 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 B and so on. It may be A, B, B, B and so on, right. So, basically there is a finite occurrence of A followed by infinite occurrence of B, right. So, here you can think this A star is basically your A1 and B omega is basically your F1I, right. This is what effectively, if I consider this in terms of the generic expression, is this, right. So, here this has a finite occurrence regular expression, this is B is another regular expression which has infinite occurrence. So, F is basically F1 is basically B and A1 is basically A. Similarly, if I write this, it means what? You have A or B has a finite occurrence followed by infinite occurrence of A, right. So, you can think about that, it is A, B, B, A, B and then you start A, right. So, this is basically coming from A or B star, A or B star. It means either A or B can occur a finite occurrence of time, right. So, they are A, B, B, A. So, you can have any occurrence, right. It can be only A followed by A. So, this is basically finite occurrence and this is infinite occurrence, right. And then it can have only B, B, B then A and so on, A, B, many combinations, right. All combinations in A, B, but it is a finite length followed by infinite occurrence of A. So, you get an idea what is infinite words, okay. Now, the question is that how do you actually accept the infinite words? Finite words we have already defined, that if it basically for a finite word, a DFA accepts the word when the word ends the final accepts when the word ends in the final state. That is what I say. So, when I read the entire word, I reach the final state. But when the word is infinite, how do you accept? Because it will never end, right? I will not ever able to reach the end of the word. So, I cannot just define that the acceptance the way I defined for DFA, right. So, here we have another example for DFA. So, here this is the DFA. So, what kind of word it will accept? It can accept B, right. Then after B infinite occurrence of BB, right. So, it can be this BB, BBB and so on, and we also have a precede by A star. So, it is basically A star B B star, right. This is the kind of words, all combinations can be generated through this, is accepted by this. So, these are all finite words, right. But then the question is that how to define the acceptance of infinite word. So, it is basically because it is an infinite word, I cannot go end of this. It is the definitions of acceptance in Büchi automata is that if a word infinite word is accepted by a Büchi automata, if the finite states is visiting infinitely often for this word, right. So, the acceptance is if some final state is visited infinitely often in that automata. So, then I will say that particular infinite automata or word is accepted by that particular Büchi automata. Okay. So, let us give an example here. So, I have so this the state machine is similar to the Büchi automata will also look similar to DFA, because it is just a state machine, right, automata. It is only things that the acceptance condition is different from DFA, right. So, let us take this. So, if I try to define the acceptance the word for this corresponding to the NFA finite words, it is basically A or AB can happen, right. So, A or AB star, right. So, it can have A or AB, any combinations of them, and then but followed by you have to have A, right, because you can have any number of A here or here, but finally you have to take a to go to this final state. So, any combination of this is basically accepted by this NFA or the finite words. Now, what are the kind of infinite words this automata can accept, right. So, we told that the word should be of infinite length and you have to visit this final state infinitely often. So, if you think about that, to visit this you are starting from this state, and if you try to come to this infinitely often, so you have to have this loop infinitely often, right. So, you have basically all the infinite words where there will be infinite number of occurrence of AB, right. So, the language of this omega is, if I consider this as a Büchi automata, then the language that will be accepted by this will be this, which is basically all combination of the word where AB occurs infinitely often in this, right. So, to give an example, you can think about that I have A, AB, AB, right, then you have A, then you have A. So, basically you have one occurrence here, then you go this, you do this one round, right, and then you do another round here, and then you basically have 3 times in this loop, and then you keep doing this, right. So, which is basically this A and infinite. So, this is one word, but this is infinite, but this word is accepted by this because with this this should be AB, AB. So, whenever you are doing this AB, so you are basically for every AB you are effectively coming back to the final state. So, that means if this AB repeats infinitely, so you have a infinite occurrence of this occurrence of the AB. So, that means you are visiting this final state infinitely many times. So, this kind of word will be accepted by this if I consider this as a Büchi automata. Okay. So, you can see that for the same automata if I consider this as an NFA, the word is different, the kind of word that is accepted by it is different from if I consider the same machine as a Büchi automata, then the word that will be accepted by the same model will be different because the acceptance condition is different for both of them, right. So, why we need this NBA, GNBA? We have already talked about that we need to construct a GNBA corresponding to this LTL formula. So, we need to understand that, right. So, we basically from LTL formula we construct the GNBA first, from GNBA we will convert to the non-deterministic Büchi automata, and then I will create the product automata with the transition model, and then I will do the verification, right. So, we need to understand these things. So, let us now define what is deterministic Büchi automata and what is non-deterministic Büchi automata. So, from this slide you get an idea that it is simply a finite automata, just like a normal DFA, only the acceptance condition is different, right. So, now if I go into this deterministic versus non-deterministic Büchi automata, so the automata is basically have the non-determinism in the case of non-deterministic Büchi automata, and the transitions are deterministic in the case of deterministic Büchi automata, right. So, if you come back to this model, this is NFA, because you have in this state, in the state of S0, if you give A, either it will rotate, if you give A, it will come back to S0, or it can go to S, right. So, effectively this is the non-determinism. So, for the same input you can have multiple transitions. So, you can have multiple run for the same input, right. So, this is what non-determinism, whereas in the deterministic Büchi automata or deterministic model, for every state, for every input you have only one next state, right. So, for example, in this is a deterministic one, because if you give A here, you are coming here, if you give B, it is going here, and this is for this also you have to define what is going to happen for A, right. So, this is deterministic. So, the difference between deterministic and non-deterministic is there is a non-determinism in the transitions, right. So, the multiple next state is possible for the same input symbol on a state. On a deterministic Büchi automata, for every state, for every input symbol, there is exactly one next state, right. This is well understood, but that is not only the difference. The other difference is that because in a deterministic automata, if you give a word, infinite word, it will only go through one path, right, because for every input there is only one transition is defined. So, it will always get a one trace, right, or one run, right. On the other hand, in the non-deterministic, because if you give A, you can go to this state or that state. So, you can, for a given infinite word, you can have many run, right. Then how do I decide that whether this particular word is accepted by this Büchi automata? For deterministic Büchi automata, you have since a unique run, I will say that the word is accepted if that particular acceptance state or the final state is visited infinitely often by that run, right. On the other hand, because in non-deterministic Büchi automata, you have multiple such run, at least one of the runs should visit the accepting states infinitely often, right. So, the word is accepted if at least one of the run visits the accepting state infinitely often. There may be multiple run, but at least one of them should visit the accepting states infinitely often. And for deterministic Büchi automata, because for every word there is a single run, we have to just check that run visit the accepting states infinitely often or not, right. So, this is the difference between deterministic and non-deterministic Büchi automata. So, are they equivalent? It is actually not. So, they are not equally expressible. In DFA and FA, they are actually equally expressible, but this DBA and NBA, deterministic Büchi automata and non-deterministic Büchi automata, they are not equally expressible. Okay. So, let us try to understand that with a simple example. So, let us take first a DBA, deterministic Büchi automata is this, it is just like a simple DFA. Only thing is that I have to identify the word that will visit the final state infinitely often. Why it is deterministic? You see here in Q0, if you give A, you have only one transition defined to Q1. If you give B, it will come back to Q0. So, for every input, there is a unique transition. For Q1, if you give A, it will come back to Q1. If you give B, it will go to Q0. So, again for Q1, for each symbol, you have a single transition, right. So, effectively, this is deterministic Büchi automata. Now, let us understand what kind of word it will be accepted by this. It basically, if you are starting from here, you have to visit Q1 infinitely often. So, effectively you have to be this loop occur infinitely often, which is basically AB. So, any word that is accepted by this DVA will have a infinite occurrence of AB, and you can have other B and A string in between, but you have to have AB and infinite occurrence, right. This is well understood. Now, take one language, say I want to create automata, I want to construct a Büchi automata corresponding to this. Can I construct a deterministic Büchi automata? So, what is this? Here I am having a finite occurrence of 0 1 followed by infinite occurrence of 0, that is this word mean, right. You have a finite sequence of 0 1 followed by eventually an infinite number of zeros. Now, so if you give an example, so you basically have an infinite occurrence of 0 here, and in this is coming from 0 1 star, right, and this is coming from 0 omega, right. This is how we will say, and this is not accepted because here there is no infinite occurrence of zeros. Okay. So, now let us try to see whether can I construct a DBA corresponding to this or not. So, answer is it is not possible, because what is happening here. So, you basically have, you can think about a automata like this, where your 0 1 1 is having infinite occurrence here, any combination of 0 1 followed by you take this 0 and then you infinite time you rotate here and then you get infinite occurrence of 0. So, this is one Büchi automata that is accepting this particular language. The language is 0 1 star and then 0 omega, right. This is the language that is accepted by this, right. Why? The 0 1 star is realizing here in this Q0, and then you have a 1 0 definite and then you have infinite word of zeros. Is it a DAB? It is not DBA, right, because you have for 0, right. So, if you take 0, you have a transition here, and for the same 0 you have a transition to Q1 from Q0, right. So, effectively this is not a deterministic Büchi automata, this is non-deterministic Büchi automata. So, I am able to construct a non-deterministic Büchi automata that accept this language, but can I construct this DBA? The answer is no. Why? Because you do not know the length of this 0 1 star, whether this will be length of 4, length of 5, length of 6. So, that particular thing I do not know. So, I do not know how many times I will rotate here. In a deterministic model, you need to know that the length of this, right, and since that is not defined, it is kind of a, this can also be very long, right, it is finite length, but it can be very long, very length. So, this part cannot be accommodated by a DBA, because you have to have this non-determinism between these zeros, because I do not know which 0 is actually eventually take away the infinite occurrence of 0, right. So, the next 0, whether this is going to the infinite occurrence or I will have another one after that I do not know when I reading the string at some point, right. So, for example, if you say 0 1 0 1 0 0 0 0 0. So, when I am reading this 0, I do not know whether how many ones are there. If I reading this 0, I do not know this is the starting of the infinite zeros, right, because there is another one. But when I am reading this, then it starts, right. But this, when I reading from this way, from the input in one character at a time, I do not know how many ones are after that, right. So, that is why this determinism cannot be modeled here. So, I cannot model this particular any DBA corresponding to this language. Okay. So, they are not equally expressive. So, let us define what is NBA formally. So, it is, you have already seen model. So, it is basically have set of states, you have set of input alphabets, and then you have some state Q0 which is the initial state, and F is a set of accepting states or the final states, right. It is a subset of this Q. This is important. Here you have, if you give, you are in a state, if you give an input, you will get a subset of next state, right. In a DAA, the everything will be same, only the delta will be Q into input to Q, right. So, you will go to one input, right. If you give a state, if you give an input, it will go to another state. Here it is power set. So, it is basically some subset you will go corresponding to every state for every input, right. So, this is the formal definition. And I have already defined the accepting runs, it is one of the run for the input accept. So, let us define that formally. So, you have basically in a run in a NBA is basically an infinite sequence of states, right, and which follows the transition effectively, right. So, if you are in Qi state, if you give the AI input, it will go to Qi plus 1, okay. And so, this, so if you take this run, you will get a word, right, because every transition associated with a alphabet. So, that will be the infinite word corresponding to an infinite run. So, every run will have corresponding word, but since here you have non-determinism, for every character or every alphabet you can have multiple transition. So, for every word you can have many runs, right, and we have defined that that at least one of the run is accepting, that means it is visiting infinitely often the final states. So, effectively here this is defined by like this. So, INFP is the denote the set of states occurring infinitely often in this run, and these are the accepting states. So, their intersection should be not phi, right. So, effectively it means basically that at least one of the run has infinite occurrence of this the final states, right. So, this is what we have already discussed, and the language is basically the infinite words that accepted by NBA if there exists an accepting run for this, right. So, there can be multiple run, at least there exists one accepting run corresponding to this word which visit the final states infinitely often. I think that is clear, right. Then again, why NBA is important, you already know that. We initially construct a generalized non-deterministic Büchi automata, and then I will convert this into MBA, right, and then I will construct the product automata. That is why this NBA we have to understand, and since this DBA is not sufficient, some cases cannot be modeled as GBA, we will take NBA in our formulation. Okay. So, we have not discussed what is GNBA yet, right, generalized non-deterministic Büchi automata. It is a special class of NBA. So, in today's class what we have learned so far, we have learned what is regular language, omega regular language, then what is Büchi automata, what is the acceptance condition for the Büchi automata, and then what is deterministic and what is non-deterministic Büchi automata, right. But we have not learned what is generalized Büchi automata and how do we convert a generalized Büchi automata to NBA, and then what is the core intuition of having a LTL formula, what is corresponding GNBA. So, this part we have not discussed in today's class, and that will be the topic for the next class. Okay. Thank you.